Hey guys, today we want to introduce you to random variables. Every day, we try to operating with a human-readable description of an entity, and numerical entities permit to solve this problem. In fact, the need to translate the description of events to use the full tool of mathematics is the reason behind the birth of random variables. To be formal, a random variable is a function of an outcome, x equals f. In other words, it is a quantity that depends on chance. When using numerical structures, the specific behaviors of different events can be analyzed in depth. Expectation, variance and covariance are all results of this type of analysis. They all involve studying sequences of random variables to better understand how certain realities behave. Through random variables, it is possible to observe how specific outcomes are distributed. The main purpose of simulations is estimating those quantities whose direct computation is complicated, risky, consuming, expensive, or impossible. For example, suppose a complex device or machine is to be built and launched. Before it happens, its performance is simulated, and this allows experts to evaluate its adequacy and associated risks carefully and safely. With the help of random number generators, probabilities can be estimated by a mere computation of the associated observed frequency. Similarly, one can estimate expectations, variances, and other distribution characteristics from a long run of simulated random variables. Now we want to talk about the generation of random numbers. There are a lot of RNGs, but in this video we are going to talk about pseudo-random number generators and true number generators. First of all, we need to analyze some properties of the sequence that each RNGs generate. The goal of an RNG is to produce a well-distributed uniform random numbers, and for that we need each number appears a maximum of once within the sequence. For the deterministic random number generator, the length of the sequence represents the period of the sequence. For the deterministic random number generator, the only secret is the seed. The algorithm is known. Let's start talking about true number generators. This type of generator can be represented as a function connected to hardware devices to extract unpredictable data from physical phenomena. Naturally, the definition is clearly too abstract, but it conveys the idea behind this type of generator. The unpredictability of data is closely linked to the concept of entropy. Entropy is defined relative to one's knowledge of an experiment's output prior to observation, and reflects the uncertainty associated with predicting its value. The larger the amount of entropy, the greater the uncertainty in predicting the value of an observation. Of course, a hardware random number generator is expected to output near-perfect random numbers. Because true random number generators are often computationally expensive to generate, they are often used to generate the seed of PRNG. Let's talk about a pseudo-random number generator, and in particular about the linear congruential generator. A PRNG is an algorithm that uses mathematical formulae, or simply pre-calculated tables, to produce sequences of numbers that appear random. An LCG produces a series of pseudo-random numbers using a discontinuous piecewise linear equation. This method is among the oldest and most widely recognized algorithms for generating pseudo-random numbers. The generator is defined by the recurrence relation. According to this, the maximum length of the sequence is m, but it is only possible if LCGs are fast and require minimal memory to maintain state, and are very useful in embedded systems where memory space is limited. The high correlation is not good for Monte Carlo simulations, and they are not suitable for use in cryptography applications. Let us now look at the main properties of pseudo-RNGs. Determinism. Seed is the key of the PRNGs and permits to generate the same sequence. An incorrect seed initialization can lead to always get the same sequence of number, but it can be very useful for replicating a specific situation at different times. At the same time, if the algorithm is deterministic, by knowing the algorithm and the current state, the next number can be predicted. Periodicity. Another characteristic that distinguishes PRNG from TRNG is their periodicity. The sequence will eventually repeat itself. This is a hardly desirable characteristic, but, fortunately for us, Modern PRNGs have a period that is so long that it can be ignored for most practical purposes. One would like the cycle length to be longer than a typical run. Uniformity. The uniformity property is the one that verifies that a RNG outputs follow a uniform distribution. This property means that if we go through a complete cycle, all the integers occur once. Correlation. For a RNG, it is important that there be no correlation between two numbers generated, as prediction of the next number can lead to security problems. Efficiency. Efficiency is the property that more than others is in favor of pseudo-RNG, because in a short time a pseudo-RNG can produce many numbers. This can certainly be advantageous for all kind of application that need many number in a short period of time. Now it's time to analyze the RNG results. First we need to describe two methods that allow us to analyze our results, the dot plot method and autocorrelation. The dot plot analyzes the similarity of two sequences and allows you to see them graphically. This method tries to compare the distance between planes. The further away they are, the worse the generator is. Autocorrelation allows the random sequence to be interpreted as a particular path of the ensemble of a stochastic process. Given this interpretation, time series analysis is available. No autocorrelation is what a good random number generator should aim for. The first analysis involves a simple algorithm which, by implementing the basic formula for producing an LCG, generates a sequence of distinct numbers. All we have to do is choose a prime number, a numeric seed, and the generator. The prime number is the modulus, while the seed is the first number that the algorithm will produce. So we have already seen that the sequence can appear random only if the observer does not know how it was generated. So we choose 8191 as the module, 1001 as the generator, and the two seeds will be 42 and 142, so as to produce two different sequences. As we may expect from sequences produced by LCGs, the dot plot shows the specific linear structure of the two sequences, and this clearly highlights that true randomness is completely lost. The sparser the graph, the more random the sequence. When using a noise source, there is an expectation that the results cannot be predicted. For our purposes, the sequences proposed by Randomness and Integrity Service will be sufficient to compare them with the previous ones. Since it is not possible to calculate a pure function to predict atmospheric noise, this method should be sufficiently reliable. A scattered dot plot is expected with no visible similarities between the generated numbers. Although TRNGs are assumed to be aperiodic, this sequence of numbers can be classified as lottery tickets drawn from a hat. Since methods that only use external sources to generate random numbers are too expensive for some types of applications, there may be ways to combine them with some degree of compromise. The combined generators are composed of the following piece. The generator itself, the entropy accumulator, which collects truly random data from various sources and uses it to reseed the generator when enough new randomness has arrived, and the seed file, which stores enough state to allow the computer to start generating random numbers as soon as it is available. The main idea is to generate a random key using a real random number generator and XORing it with each number generated by an LCG. Since a true random number can be part of the state of the algorithm, several sequences can be generated without changing the seed. However, the results are not so satisfactory. Using the generator in the usual way, the result obtained is more convincing. However, some sort of pattern is still visible. What about autocorrelation? Autocorrelation mainly occurs in time series. It will be enough for us to say that in the absence of autocorrelation, subsequent vertical bars would quickly drop to near zero, or at least between the dashed blue lines of the plotted estimates. The first two plots represent the autocorrelations for the LCG sequence and the mixed one. At first glance, the first two sequences appear to represent different correlations. The only difference is its level of significance. By introducing a noise source, XORed with the pseudo-random number, the correlation is simply scaled down, not eliminated. In a sense, this tells us that even if a sequence has a low level of autocorrelation, it can still be autocorrelated by changing our magnitude of the observation. Since the example above does not show a rapid decline in correlations, some autocorrelation may be present. In the last graph, the subsequent correlations tend to zero and remain within the limits of the significance level, represented by the dashed blue lines. Therefore, it can be assumed that there is no autocorrelation. Since how random numbers can be generated using computers is a very complex field, no solid conclusions can be drawn since only the surface has been covered. However, the use of relatively simple techniques such as LCG allows a complete generation without repetition of very long sequences, and for this reason it is possible to carry out simulations. However, since determinism is a key property, truly unpredictable sequences are out of the question. By using appropriate sources of entropy, it is possible to achieve true randomness, as always trade-offs may arise. Finally, combining techniques could be the solution, although random data collected during the process must be used to alter the internal state.